Hello, so today I'm going to talk about my project, which is comparing AI decision making with expert biomarker. So here I'm trying to see whether the decision made by AI is consistent with the decision made by doctors or not, right? And then this is a case study on diabetic retinopathy classification presented to you by me. My name is Ayusma, and it was advised by Professor May. So first we need to understand what is this diabetic retinopathy, right? So it's a eye disease and it is a type of eye disease that is caused by damage of blood vessel. You can see here due to the damage of blood vessels, all these blood is being leaked. So this is a problem called diabetic retinopathy. Note that this is due to the diabetes. It happens in the diabetes patient. And to compare between healthy eye and diabetic retinopathy, you can see the blood vessels and everything they look normal, right? There's no external leakage of blood. There's nothing sort of some traces or anything. But if you see in the diabetic retinopathy, you can see here abnormal growth. It was supposed to be like growing like this, but it grew abnormally, and you can also see the blood leakage, which is hemorrhage, cotton wool spots, and so on. So, in the statistics, it is seen that 400 million people are having a problem of diabetes disease, right? And from 400 of them, 161 million out of 400 are developing diabetic retinopathy. How severe is that? It's like around half of the people with diabetes are supposed to have diabetic retinopathy along with diabetes. It's sad, right? And it is also mentioned that the global blindness is supposed to increase, like the cost of the global blindness which is caused by diabetic retinopathy is 2.5% from total, like from 100 people, 2.5, two and a half of them will have diabetic retinopathy. And the source is International Agency for Prevention of Blindness. And the thing is, another terrifying news is it is predicted that the vision loss will increase by 50% in upcoming 50-year span. But then how can we control it, right? It's just increasing and increasing and increasing. If you do not have any controlling process, then it will be really a sad situation. So we need to control it, but how, right? But the good news is if we were if we can do the early treatment up to 95%, 95, that's a huge number. We can prevent vision loss by 95% if and only if we can do the early treatment. The traditional method for seeing and to classify whether the patient had diabetic retinopathy or not is go through the doctors, go to the hospital, and they will perform some eye dilation techniques, and it will consume a lot of time and energy. And due to the latest advancement in AI and technology, we are trying to use AI to predict the disease. So this is the latest advancement, but you might be considering why do we need AI over traditional method, right? The thing is they can identify subtle patterns in medical images. Note that this is a very tiny part of our whole body, like comparing to our face or comparing to our heart, kidney. This eye, it's very small in size, so it will be very hard for the humans to see whether it had some problem or disease just by looking at it. So that's why an AI, they can identify the very tiny little patterns in medical images, which is very useful in predicting the disease. And they're also being very accurate and they take certain amount of time. So that's why people are using AI. The pain points the pain points of the project is there is a lack of interpretability. Like they are using AI, but then they are not interpreting. The AI is not interpreting it. It is just classifying disease, but we do not know why and how it is classifying certain things as this and why not. And there might be some misalignment and which will there in fact impact on healthcare outcome. So we need some solution. So the main objectives of our project is to classify the diabetic retinopathy using AI and visualize, and then we want to compare whether the features extracted by AI is similar or same with the features that are used by doctors to perform and classify the disease. And we are trying to validate the alignment statistically using z-test. So first, I'd like to talk about the data set that I use. So it is a public open access database, which is FGADR. It was provided by the authors right here. It contains 1,842 images, and the features of this dataset was it was pixel level annotation by ophthalmologist. In the paper, it was mentioned the 5 different doctors. They did the manual annotation, and then it was processed with the OpenCV and other advanced software to do the segmentation. And you can see here we are using 6 biomarkers like this. This is actually the boundary box drawn by the ophthalmologist. This is soft exudate neovascularization in hemorrhage, like the blood leakage, microanesia, and so on. We did the 80-20 split and we use 5-fold validation. This is our proposed workflow. At first, we started by data collection using this website, actually the research paper, and then we did data augmentation followed by VCZ followed by LRP to generate heat maps, and it was followed by z-test. So there are 5 stages of DR. Okay, the first is normal, mild, moderate to severe, and proliferative. So we are classifying the DR into 5 stages, whether it's normal, mild, moderate, severe, or proliferative. For the classification, we use our traditional VCC model, which contains convolution, ReLU, max pool, fully connected, and softmax. This is the structure of VCC. And now you might be thinking, why don't we use advanced model like ResNet, Inception, MobileNet, right? Actually, we use VCC because it was very simple to use, and we also tried using the advanced model, and to be honest, the accuracy was exactly the same as VCC. So why do we need to use more computation charts if we can get the same accuracy? That's why we went with the VCC. And another main factor is because it was compatible with LRP. Since VCC is a sequential model, it goes layer-wise layer, and we need to use that layer-wise layer, all those calculation in the LRP. So it went along with LRP, so we use VCC. And for your information, we did not use ResNet or other models because they have the skip connection, right? And if we use the skip connection, we cannot trace it back. So makes sense. So we did not use other model. Now let me explain why did I choose LRP and how it works. Sorry. Okay, so the classifier, it will classify the input object. In our picture, it is a rooster. So it will classify, oh, hey, it's a rooster. I predict this as a rooster, but we don't know how. What is it predicting? The LRP here, it will go through the image and it will find the feature. It will find because of its red comb, throat wattle, secondary indicators, like what makes it a rooster. So it will see those patterns and then it will just generate the heat map so that we can understand why is it predicting it as a rooster. This is our classification model which will predict, and from the prediction, right, from the predicted probability, we will go back into the model like backwards and then see the relevance of each neuron with respect to another. So in this layer, we see the how how much relevant this neuron is to generate the output. And then if it is relevant, we go through that path. If they are not relevant, like here, we skip it. Like we just like how do I say? We just disregard it. Okay, this neuron was more relevant, so we followed that path. These two are less relevant, so we skip it. And then we can trace it back and we can get through the input image, and you see this pixel and this pixel were used to make to classify, right? So we are gonna generate heat maps right here, and the severity of heat map, it is dependent on the relevance score. If the relevance score is higher, it will be red, like as you can see here, the relevance is high, so it is red. If the relevance is low, it will be blue. If it is not relevant at all, it will be all black, like nothing. And this is the mathematics behind LRP. This is used to see the relevance of each neuron with respect to other neuron in that particular layer. And if the relevance score is positive, that means that layer was used to make the classification. And if it was negative, it was used against the prediction. That means it does not provide any valuable insights into making the prediction. If we do not have that layer, it won't matter because we did not use it. Simple logic. And this is the results. Heat maps, all these heat maps shows where the model looks to make prediction, right? So you see heat map generation is here and then here, but this is more reddish. That means this is more important. So the computer, the AI will look there, look here to make prediction. And this is the ophthalmologist and doctor's prediction, class 2. Why? Because due to the presence of hemorrhage, hemorrhage is a biomarker used to classify diabetic retinopathy as class 2. And you can see here, it is present here, and they drew a boundary line over there to make it visible for us, like non-doctors. And this is AI. AI, you can see AI also used the same exact place, exact location, which was used by doctors, right? And AI also predicted this as class 2. Why? Because these neurons were, were more relevant in making the classification than other neurons. So it was higher relevant. The pixel containing hemorrhage information, they were more high relevant than other pixels. So it used that relevance score to generate the heat map and classify. So do AI and doctors think alike, right? So you can see here from the results we obtained 165 out of 266 prediction were correct. So we can see that, oh yeah, AI looked the same thing as doctor used. But how do we prove it? We need some proof, right? So for the statistical test, I use z-test because of the proportion here. And the expected proportion was random, right? Like if AI was not working, it will just generate some random probability, like true or false. It will just say either it's true or false. So it will be 50-50% chance. And then our null hypothesis and alternative hypothesis was that. And you can see here the p-value is significantly lower than our significance level. So we can say we can reject the null hypothesis and say that AI and expert alignment is significantly greater than random because of the p-value. And this is the results from our data. The accuracy was 77%, but due to the class imbalance, let's talk about FN score. This is more, this gives more generalized information. So our overall accuracy is around 67%. And to discuss, AI was able to match with the human reasoning. But the thing is, it is still weak at class 0 and class 4. Why? Because class 0 and class 4, it contained multiple lesion area. So it was confused whether to classify this as 3 or 4. So it was not predicting well. For class 0, it was no diabetic at all, right? But then the image in class 0 looked kind of similar to the diseased one, so it was confused, maybe. Here comes an interesting question. Should we trust AI more if it sees the things that doctor miss? Because we have some human errors and our visualization is limited to our two eyes and other microscope or any other external device. But AI, it can see the very tiny details. So should we trust AI or should we trust doctors? This is some interesting question. You can just think about it. And there is no right or wrong answer for that. For the limitation, we have some, as I mentioned earlier, some of the images contain mixed lesions, so AI was confused whether to classify it as A or B. And we compare the manual heat map by ourselves, by my advisor and I, so it is subjective. Normal images were like disease 1 for class 0, and for few of the classes like class 4, we had very small sample. So all this limitation resulted in a lower accuracy. As a future work, we would like to try advanced model to improve accuracy and use advanced version of LRP, which is CRP, and expand dataset and make it diverse. So the clinical impacts of my project is obviously it will build the trust because won't you be more comfortable using AI? That's just why it made its decision rather than just believing it unknowingly. And it will also encourage explainable human aligned AI tools in diagnosis, especially in diagnosis. And people can trust as well. To conclude, we use VGG16 with LRP, and it was significantly proven that AI focused on the same thing as doctor use. So it is more transparent, more explainable, and it's more trustworthy. Thank you so much for your attention. I hope you enjoyed. And if you have any question, please do not hesitate to talk to me, reach out to me at my provided Gmail address. Thank you again for listening. See you again.